This video is for the Chapter 3 review regarding logarithms and exponential functions. This first set of problems is all about logarithms and using those properties of logarithms to expand them into several different logarithms. So for this first problem, we have the log of 3 to the x. Remember, without the base written, we assume that this is a base 10. So we assume base 10 logarithm, which not too important for this particular problem. But if we have the 3 times x in the middle, we can separate this into two logarithms that are added together. The log of 3 plus the log of x. So anytime we multiply on the inside, we can add those logarithms together. Both those logs are positive. But if you look at number 2, we have the 4 and the y on top, but we have the x on the bottom. So one thing to remember is anytime the numbers are on top, or the variables are on top, the logarithm is going to be positive. If it's ever on the bottom, the logarithms are going to be negative. So in this case, we have the log base 4 of 4. So that's a positive log because the 4 is on top. The y is also positive, plus the log base 4 of y. But the x is on the bottom, and so we need to subtract the logarithm that has the x inside of it. So the log base 4 of 4 plus the log base 4 of y minus the log base 4 of x. We can simplify this further looking at this log base 4 of 4. Remember, if we're looking at the log base 4 of 4, we're trying to answer the question, 4 raised to what power is equal to 4? That's what these logarithms are telling us. 4 to what power is equal to 4? And of course, the answer to this is x equals 1. So the log base 4 of 4 is just 1. So we have 1 plus the log base 4 of y minus the log base 4 of x. And that is our final answer for number 2. For number 3, I'm going to jump down to the bottom here. We have the natural log of e to the 7th, x squared, and y to the 7th. Because we're multiplying all of those together, we can write them as 3 separate logarithms added together. So the natural log of e to the 7th plus the natural log of x squared plus the natural log of y to the 7th. Then all of these exponents, because they're inside of a logarithm, we can swing out to the front of each term. So we end up with 7 times the natural log of e plus 2 times the natural log of x plus 7 times the natural log of y. We aren't quite done. There's one more thing that we can do. Look at the natural log of e. Similar to what we did over on the left with the log base 4 of 4, the natural log of e is a log with a base of e. So if we take the log base e of e, that's just going to equal 1. And so this ends up being 7 times 1, which is just 7. 7 plus 2 times the natural log of x plus 7 times the natural log of y. So this is the answer to number 3. For 4, 5, and 6, it's a similar process, except now we're doing the opposite. Instead of separating them apart, we're putting everything back together. And so for number 4, for any of these actually, if the logarithms are positive, the number goes on top of the fraction. If the logarithms are negative, they go on the bottom. So in this case, the 2 natural log of 3, we can start by bringing the 2 up as an exponent. So that's the natural log of 3 squared. We can do the same thing with the 4 and the x, minus the natural log of x to the 4th. Because the natural log of 3 squared is positive, that's going to be, the 3 squared is going to be on top of the fraction. Since the natural log of x to the 4th is negative, this is going to be on the bottom of the fraction. So when we squish these together, we get the natural log of 3 squared on top divided by x to the 4th on the bottom. We can further simplify this by actually doing 3 squared. So natural log of 9 divided by x to the 4th. Number 5, both of the logs are positive, and so there's going to be nothing on the bottom of the fraction. We can bring the exponent up, so that becomes y squared. So bringing these together, we get the log base 4 of the x, and then the y to the second. Nothing else to do with that. Then for number 6, the positive logarithms will be on top, the negative logarithms will be on the bottom. And then bring up all the exponents. So for the middle term here, this gets its x to the 6th power. The last term, we get 3 squared. So we have the log base 2 of the 5 goes on top, the x to the 6th power goes on top, and then with the minus 2 log base 2 of 3, this one's going to go on the bottom, the 3 squared, once we bring that exponent down. Which, of course, we can simplify into the log base 2 of 5x to the 6th divided by 9. So for problem number 7 here, we were looking at writing the equation of an exponential function through 2 points. Letter A is actually somewhat straightforward because we're given the y-intercept. But for part B, it's a little bit more complicated. So let's take a look at these. So for A, remember we're trying to get a form y equals a times b raised to the x power. So if we plug each point in separately, we get 2 equations. We get 5 is equal to a times b to the 0, and we get 2 equals a times b to the 3rd. We now have a system of equations in 2 variables, a little different than the linear systems that we did back in algebra, but still doable using similar methods. Here, for the first equation, we have b to the 0 power. Fortunately, that's just equal to 1. So right away, we know that a is equal to 5. So now that we know a equals 5, we can plug that into the second equation and solve this for b. So 2 equals 5 times b to the 3rd. Now, don't get thrown off by this just because it's in the context of an exponential function. All we need to do is divide by 5. And then if we have b to the 3rd, just take the cube root of both sides. So we need whatever the cube root of 2/5 is. Now remember, the cube root button is underneath the math button on your calculator. So cube root of 2 over 5, we get b equals 0.737. So to write the equation of this exponential function, we need to just plug that a and b into the original piece that we have up here. So our final equation, we get y equals 5 times 0.737 raised to the x power. For part B, we do the same initial setup. So we have 3 is equal to a times b to the 2nd power. 31 equals a times b to the 5th power. So here we don't have a b to the 0, so it doesn't cancel out real nicely for us. But we can solve one of these equations for a. Doesn't matter which one. We can do the first one. So divide both sides by b squared. We get a equals 3 over b squared. Now that we know what a is, we can substitute it in, just like we did in the first problem. But now we substitute that b in as well. So we get 31 equals 3 over b squared. And then we still have the times b to the 5th. I'm just going to put that on top of the fraction. By multiplying that on the top of the fraction there, we can see that there's some b's that will cancel out. We can cancel out a b squared on the bottom with a b squared on top, and it turns into 31 equals 3b to the 3rd. So we cancel out two of those b's on the top and the bottom. Well, now it's just similar to the problem we did earlier. Divide by 3, take the cube root. So we get 31 over 3 equals b cubed. The cube root of 31 over 3, let's try this out here. We get 2.178. This is our b value. We still need the a value, but remember we have a formula for that up top here. So we just take 3 divided by that b value squared. So a equals 3 over 2.178 squared. And we get an a value of 0.632. So we now have that a and b value. So our final equation, we get y equals our a value, 0.632, times b, 2.178, raised to the x power. That exponential function contains both of those two original points. So solving a system, setting these up, and getting that final equation. Number 8, 4 different parts here, and be able to do the formulas for each one of these. So we start with $12,000. We invested at an 8% interest rate, but we have different conditions for each of these. Whether it's once a year for 5 years, quarterly for 15 years, daily for 10 years, all these different situations, and we need to figure out what each one's worth. So we always use this formula here, the P times 1 plus R over N raised to the NT power. So for part A, we start with our initial amount, 12,000, times 1 plus 0.08 divided by the N value is the number of times per year. This is annually, so it's only going to be once per year. And then the NT is just 1 times whatever the time is. In this case, it's 5 years. Be careful how you type this into your calculator. You don't want to mistype anything. But we do end up with a value of 17,631.94. For part B, we use the same formula, but now we're doing quarterly. And so our N value is going to be 4. So still the 12,000 times 1 plus 0.08. But now instead of divided by 1, we're going to divide it by 4. And then raise that to the 4 times the NT. 4 times 15. Again, type this into your calculator, and we get 39,372.37. Part C, same formula, 12,000 times 1 plus 0.08. But now we're doing this daily, which means that our N value is 365. So 0.08 divided by 365. But then we have to raise that to the 365 times 10 because we're doing it for 10 years. Type this out and we should get 26,704.15. I hope it doesn't bother you that I switched from boxes to circles. For part D, compounding continuously for 20 years, we have to change the formula here. Once we're doing it continuously, this is where we use our PERT formula, P times E raised to the RT power. So we take our initial amount, 12,000, times E raised to the RT, so 0.08 is our rate, 8%, times the time, which for this piece is 20 years. Type all that into your calculator, and we end up with 59,436.39. The next several problems are all about these exponential growth and decay kind of applications. So make sure you can write out these formulas here. So we started with 285 cell phone subscribers. And the number of subscribers is increasing by 75%, so 1 plus 0.75. And we'll raise that to the x power. I want to know how long will it take for the number of cell phones to triple. So if we want the cell phones to triple, if we start with 285, then triple that is 3 times 285. So simplified, we get 285 times 1 plus 0.75 to the x is equal to 855. Now to solve this for x, the first thing that we need to do is divide both sides by 285. Cancels out on the left, we have 1.75 to the x is equal to 855 divided by 285 is 3, because we're tripling. Now is where we have to start using logarithms. In order to get this x out of the exponent here, we need to take the log of both sides. So we have the log of 1.75 to the x equals the log of 3. Now we can swing this x out front. So we get x times the log of 1.75 is equal to the log of 3. Then to get x by itself, just divide by the log of 1.75. Those cancel. Type that right side into your calculator, and we should get 1.96 years. So it shouldn't take very long because we're growing by 75%. That's a pretty big growth, pretty fast growth, and so it's not going to take a whole lot of time to triple. Number 10, we're looking at bacteria. The alarming rate, it doubles every hour. So if we start with 1, after 1 hour it doubles, we get 2. After the next hour it doubles, we get 4, then 8, then 16, then 32. Every time we're multiplying by 2. So we take the one bacteria, we multiply it by 2 over and over and over again, and to get a full day, we have to multiply it by itself 24 times. So it's just 2 to the 24th power, which is 16,777,216. Number 11, you start with 120 milligrams of caffeine that you've now drank. And every hour that caffeine decreases in your body by 12%. So we do 1 minus 0.12, so we're decreasing 12%. And then we do that over and over again as the hours go on. So how long will it take to have just 10 milligrams left in your body? So we want this to equal 10. And now it's similar to the phone problem that we were doing earlier. We need to solve this equation for our variable in the exponent. It will require logarithms. So start by dividing both sides by 120. I know a lot of kids miss that piece on the progress check. But don't forget to divide by that 120 first. The 1 minus the 0.12 is 0.88. Might help to simplify that. 0.88 to the x power is equal to 10 divided by 120 is 0.083 repeating. So let's take the log of both sides. When we take the log of the left side, we can bring that x out front. So it's x log of 0.88 is equal to the log of 0.083 repeating. Then to get x all by itself, divide by the log of 0.88. Those logs cancel out on the left. Simplifying the log of 0.083 divided by the log of 0.88 we get x equals 19.44 hours. So, just shy of 20 hours for the caffeine to just get down to that 10 milligram level. Number 12. Your house has 1,200 termites, and they grow at a rate of 2.4% every day. We want the number of termites to double. So we want that to be 2,400. That's a double from what we have right now. So 2,400 is equal to the initial amount, 1,200. We're growing at 0.024 to the x power. And then we want to solve this equation. Divide both sides by the 1,200. On the left side, 2,400 divided by 1,200 gives us 2. I'm going to jump to the right here. 1,200s cancel. 2 equals 1.024 raised to the x power. Take the log of both sides. When we take the log of the right, we can swing the x out front. So we get the log of 2 is equal to x times the log of 1.024. And then divide by the log of 1.024. They cancel out on the right. On the left side, log of 2 divided by the log of 1.024 gives us 29.23 days. So they're not growing very fast, only 2.4% every day. So it's going to take just shy of a month for the number to double. Part B, how many termites were there 2 weeks ago? This is one of those problems that a lot of people like to miss. Well, maybe they don't like to miss it, but they do. Because they think, oh, 2 weeks ago means that we must be decreasing now. So that in my formula above, where I was 1,200 times 1 plus 0.024, a lot of kids are tempted to turn that into a minus now because the number is decreasing. However, we do need to keep it as a plus. If we just think about the graph of this, the number of termites is increasing. So we could look at 1, 2, 3, 4, 5 days and watch it going up. But if we look backwards at -1, -2, -3, -4 days, we can see that that number is going to be going down anyways. So at that point, 2 weeks ago, it was still increasing. So we still need that plus 0.024. It just happens to have been at a negative time, backwards. So we still need the 1,200 times the 1.024. But now instead of going forward in time, we're going backward in time. So we need a negative exponent. And 2 weeks ago, remember we're in days, so the exponent needs to be negative 14. 1,200 times 1.024 to the negative 14th power. And this brings us backward to about 860.96. So about 861 termites. So be careful about those 2 weeks ago, the 3 days ago. We don't want to change the function, we want to change the exponent to go backwards. So population equation, 6,191 times 0.96 to the t. What was the population in 1990? That's t equals 0. 0.96 to the 0 power is just equal to 1. So my initial population was 6,191 people. Then by what percent did the population decrease every year? This is where we look at the 0.96. Thinking population decrease, we have 6,191 times 1 minus 0.04 to the t power. So that 0.96 is that 1 minus 0.04. So the population is decreasing by 4% every year. All right, last one of these word problems. So you got land that was bought for $30,000 in 1960, and it's growing the value grows at 5% every year. What's the value of the land in the year 2011? So to go from 1960 to 2011, we're looking at a time value of 51 years. So we take 30,000 times 1.05, that's the increase of 5%, to the 51st power. And so the final value here will be $361,223.09. About 12 times what it was worth back in 1960. So then what would the price have been in 1940? So it was still bought for $30,000. That was the value in 1960. But what was it 20 years before? Now we have our time value of negative 20. This is kind of like the termite problem that we did, looking backward in time. So we still have the growth, the 1.05. Back in 1940, it was still growing at 5%. But that was 20 years ago, and so we use the negative 20 to note that. And this gives us $11,306.68. Then for part C, when was the land worth $100,000? So 30,000 times 1.05 to some time, that's what we need to figure out, but we want that total value to be $100,000. So divide both sides by the 30,000. We get 1.05 to the t power equals 3.3 repeating. Now we can take the log of both sides. If we take the log of the left, now we can swing that time out front. So t times the log of 1.05 is equal to the log of 3.3. To get t by itself, divide by the log of 1.05. Simplify that, we get t equals 24.68. So 24.68 years from 1960, it will equal $100,000. So if we add 1960 to this puts us in the middle of 1984. That's about when it'll happen. A little more than halfway through 1984. Now we get into all the solving inverse pieces. So we start with log base 5 of 2x plus 15 equals 7. So more often than not, when we have an equation with logarithms in them, we want to convert it to exponential form. So we want to take 5 raised to the 7th power, and we want that to equal 2x plus 15. So take 5 to the 7th power, subtract 15 from both sides. Divide both sides by 2. And then simplify that 5 to the 7th minus 15, then divide it by 2. We should get an x value of 39,055. For number 16, whenever we have a variable in the exponent, this is where we want to take the log of both sides. So take the log of the left side, take the log of the right side. So we have the log of 3 to the x. This is where we can swing the x out front. So x times the log of 3 equals the log of 258. Divide both sides by the log of 3. And then simplify that right side. We get x equals 5.05. 17, it's very similar to number 15, where we need to rewrite it in exponential form. But before we can do that, we need to take care of the 5 and the 3. So first, subtract the 5 from both sides. We get 3 times the log base 4 of x minus 2 equals 87. Now divide both sides by 3. So the log base 4 of x minus 2, and then 87 divided by 3 gives us 29. Now we can rewrite it in exponential form. 4 to the 29th power is equal to x minus 2. Well, 4 to the 29th power is going to be a pretty big number. But let's add the 2 to both sides. So 4 to the 29th power plus 2 is equal to x. And then if you type that into your calculator, you get 2.88 times 10 to the 17th power for my x value. So pretty big number. That's okay. It happens. Number 18. 6 to the x minus 5 power equals 36. There's a couple different ways that we can go about doing this one. One's relatively easy if you notice it, and the other can be harder if you don't notice it. So first, 6 to the x minus 5 equals 36. 36 is 6 squared. So if we have 6 to the x minus 5 equals 6 squared, those exponents have to equal each other. So that x minus 5 has to equal 2, which means we get an x value of 7. If you don't notice that, however, then right from the beginning, since we have the variable and the exponent, we want to take the log of both sides. So I'll do the second way in blue. If we take the log of 6 to the x minus 5, the x minus 5 can swing out front. So x minus 5 times the log of 6 equals the log of 36. Divide both sides by the log of 6. Those cancel. The log of 36 divided by the log of 6. Type that into your calculator. You should get 2 for your answer. Notice that now we have the same equation that we had up top. Add the 5 to both sides, we get x equals 7. So whichever way you do it, one's a little bit harder, but it sticks more with what we've been doing in class over and over again. For number 19, 5 times 4 to the x plus 3 power equals 300. Before we can do any logarithm stuff, we need to get rid of that 5. We need to divide both sides. The 5's cancel. We get 4 to the x plus 3 is equal to 300 divided by 5 is 60. Now we're in a position where we can take the log of both sides. So if we take the log of 4 to the x plus 3 power, the x plus 3 can swing out front. So we have x plus 3 times the log of 4 is equal to the log of 60. Divide both sides by the log of 4. We get x plus 3 equals 2.95. Then add 3 to both sides. We get x equals negative 0.047, if I keep another decimal place there. Then for the last solving one, number 20, it looks really hard because there's 2 different logarithms in it. One's a base 10, one's a base 6. However, the log base 6 of 643 is a number. 6 to some power equals 643. What is that power? If you type this into your calculator, log of 643 divided by the log of 6, this gives you a number 3.609. So let's rewrite the equation with that number put in. So the log of 10, log base 10 of x plus 754 minus 3.609 equals 0. So let's add the 3.609 to the other side. So we get the log base 10 of x plus 754 is equal to 3.609. Now it's just like problem number 15, where we want to rewrite this in exponential form. So we want to take 10 to the 3.609 power equals the x plus 754. So it's just rewriting it in that exponential form. Subtract the 754 from both sides, and then 10 to the 3.609 minus the 754 gives us an x value of 3,308.79. Solving inverses is very similar to solving a regular equation. The only trick is that we have two different variables going on in these types of equations. And so we need to do things a little bit differently in some cases in order to get these, to find those inverses. So remember, inverses are all about switching those x and y values. So for number 21, we have y equals 4 times e to the x plus 2. We want to switch x and y. So we get x equals 4 times e to the y plus 2. And now our goal is to solve this equation for y, get y by itself. The first thing that we want to do is get rid of the 4 that's hanging out front here. So we're just going to divide both sides by 4. So we get x divided by 4 equals e to the y plus 2. Now in order to solve this equation for y, we need to get y out of the exponent. The method that we use to do that is taking the log of both sides. So on the left side, we have the log of x divided by 4. And on the right side, if we take the log of e to the y plus 2, we can just swing the y plus 2 out front. So we get y plus 2 times the log of e. Now we could have taken the natural log of both sides, and then in this case the log of e would have canceled out. The natural log of e would cancel out. It doesn't really matter which log base we use. I just prefer using log base 10 every time. And it makes a little extra step here, but I think you'll be able to follow along. It'll be fine. So we want to solve this for y. We have the y plus 2 times log of e. Let's start by dividing both sides by the log of e. So on the left, we have the log of x divided by 4 divided by the log of e. That doesn't simplify. On the right, the log of e's cancel out, and we're left with this y plus 2. So the only thing left to get y by itself is to subtract the 2 from both sides. So our final inverse, we get the log of x over 2 divided by the log of e minus 2 is equal to y. So there's a lot going on there. But if you just take it step by step, solving one piece at a time, it shouldn't be too much trouble. For number 22, we have a logarithmic equation. We want to change it to exponential to find the inverse. So we need to start by switching x and y. So we have x equals the log base 2 of x minus 4 plus 7. Sorry, y minus 4 plus 7. So to get the y by itself, first move the 7 over. Subtract 7 from both sides. So x minus 7 equals the log base 2 of y minus 4. Now we can't touch anything inside of this logarithm yet until we write this in exponential form. So we need to take 2 raised to the x minus 7 power equals what's inside that logarithm, y minus 4. So I've changed this log form into exponential form, just like we did with the solving ones, like number 15 and 17. Then the last thing to do to get to y by itself is to add 4 to both sides. The 4 doesn't touch the 7 at all. We just have 2 to the x minus 7th power plus 4. That is our inverse. For number 23, we have y equals 5 to the x plus 3 power minus 4. Before we can in order to find the inverse, we have to switch the x and the y. So x equals 5 times y plus 3 minus 4. First, we have to add 4 to both sides. So x plus 4 equals 5 to the y plus 3 power. Now, to get the y plus 3 out of the exponent, we need to take the log of both sides. So on the left side, we have the log of x plus 4. On the right side, we have the log of 5 to the y plus 3. We can pull the y plus 3 out front. So y plus 3 times the log of 5. Divide both sides by the log of 5. The log of 5's cancel out on the right side. We're left with this y plus 3. So we're going to subtract 3 from both sides. So on the left, we still have the log of x plus 4 divided by the log of 5 minus 3 on the outside is equal to our y value. So we need to be able to do this changing from log to exponential form, taking the log of both sides, that kind of thing, using two different variables to get that y out of the exponent or out of the logarithm, depending on which type of equation we have. Next, we're evaluating logarithms. This is just our change of base formula. If we're doing the log base 4 of 2,965, take the log of 2,965 divided by the log of 4. Type that into your calculator, you get 5.767. For the next one, log base 12 of 39,205. Take the log of 39,205 divided by the log of 12. And we should get 4.25, I believe. Might be 2.6. I don't remember how it rounds. And then finally, for number 26, the log base 2 of 128. Take the log of 128 divided by the log of 2. And we should get 7 for that answer. Another way to think about problem number 26, and these kind of questions are going to be on the no calculator portion, is think 2 to what power is going to give us 128. That's what this is asking. The log base 2 of 128 equals x. 2 to what power equals that 128? Well, we have 2, 4, 8, 2, 4, 8, 16, 32, 64, 128. 1, 2, 3, 4, 5, 6, 7 2's all multiplied together. I know these are 1's. Each one represents a 2. There we go. That equals 128. Now, the ones that are going to be on the no calculator portion are a little bit more straightforward than that. But be able to do that kind of thing on this no calculator piece. Evaluate logarithms like this without being able to type it in. So the next set of problems is all about graphing these types of exponential functions. And these don't have to be terribly difficult as long as you kind of know a good general way to go about doing it. Even if the numbers don't work out nice, we can usually reason our way through a good approximation of these graphs. One approach that I think is really nice is to start by plugging in x equals 0 and x equals 1. If we can easily figure out what x equals 0 is and approximately x equals 1, then we can get a general shape for this graph. The other thing to remember is that every one of these should have an asymptote. A vertical or a horizontal asymptote at y equals 0. Unless we have some sort of vertical shifting, we should always have that vertical asymptote at y equals 0. So for number 27, if we plug in x equals 0, we get 2 times 0.75 to the 0 power. Well, 0.75 to the 0 is just 1. So we get a y value of 2. Then plug in x equals 1. We get 2 times 0.75 to the first power. You might not know exactly what that is, but if we take 2 and multiply it by 0.75, that number is going to go down. It's going to get smaller. So what does this look like in terms of the graph? Well, we know that there's the point 0, 2, And at x equals 1, it's going to get smaller. It's going to drop off on the right side and level out. Which means that on the left side, it's going to keep on rising. So even if you don't know exactly what 2 times 0.75 is, it happens to be 1.5, by the way. But even if you don't know that, at least you know that the y value is going to drop. And that tells us the direction that our graph is going to go. So if we try out number 28, we need that horizontal asymptote. And let's look at x equals 0, x equals 1. When x equals 0, we get a y value of negative 3. Negative 3 times 1.4 to the 0 is just negative 3. Then when x equals 1, negative 3 times 1.4 to the first is just negative 3 times 1.4. I don't know what it is, but it's going to be a larger negative number, like negative 5 or negative 6, somewhere in there. So multiplied by 1.4, it's going to go more negative. It's going to get bigger. So this is going to, starting at negative 3, just because we have that 1.4, this is going to grow away from that x-axis. When x is 1, it's going to go more negative. Which means that on the left side, it's going to level off. Remember, this is exponential growth, even though it's growing negative, like growing more in debt. Number 27 was an example of exponential decay. That 0.75 causes our graph to decay toward the x-axis. Number 29. Again, we need that horizontal asymptote. When x equals 0, we get a y value of negative 1. So 0, negative 1 is our point. And then when x equals 1, negative 1 times 0.4, that's going to get closer to 0. Because of that 0.4, this is decay, which means this is going to level off on that right side. In fact, negative 1 times 0.4, actually positive 1, negative 1 times 0.4 is negative 0.4. So we get closer to that x-axis, which means that on the left side, this is going to drop down to negative infinity. Number 30. Last one here, we have 4 times 2 raised to the x power. So we need our horizontal asymptote. When x equals 0, we get a y value of 4. Plug in x equals 1, we get a y value of 8. So we're starting at 0, 4, but then we're doubling it, going up to 1, 8. We can see this is going to go away from the x-axis, which means on the left side, it's got to level off toward it. So even if you don't know exactly what when we plug x equals 1 in what we get, at least we can get a general idea of that shape based on whether or not it's growth, where that number is bigger than 1, that b value on the inside, that base of our exponent. And if our base is less than 0 or less than 1, like 0.4, that's going to cause us to decay, to level off, like we have in number 29 here. So that leveling off piece is decay. The dropping down or rising up, that's growth, growing away from the x-axis. So we have 4 more of these, and again, the numbers don't work out real nice, but we can always start with a horizontal asymptote at 0. We can start by plugging in x equals 1, or sorry, x equals 0. So this is negative 1.5. So 0, negative 1.5. And then what would happen if we plugged in x equals 1? Well, this 0.5 tells us we have exponential decay, which means negative 1.5 times 0.5 is going to bring us closer to that x-axis. So we're going to decay toward that x-axis, which means going to the left, it's going to drop down to negative infinity. 32. 3 times 1.2 to the x power. Start with our horizontal asymptote. 3 times, when x equals 0, 3 times 1.2 to the 0 power is just 3. And then if we plugged in x equals 1, 3 times 1.2, I don't know what it is, but it's a little bit bigger than 3, which means that it's growth. So that's growing up, which means the left side is leveling off. 33, when x equals 0, we get a y value of -2, horizontal asymptote. And then what about x equals 1? If we take -2 and multiply it by 1.01, it's just going to be a little more negative. So it's going to be slightly below that -2, somewhere down in here. This is going to keep on dropping into those negatives. So by multiplying by 1.01, this is going to be growth. This is going to grow away from that x-axis, which means on the left side is where it decays toward it. And then 34, same kind of idea here, except now we're on the other side of 1. When x equals 0, we get a y value of 4. But when x equals 1, 4 times 0.9 is going to be slightly less than 4. So this is going to drop down toward that x-axis, which means it goes up to positive infinity on the left side. One thing to be aware of with these kind of graphs is we might give you some of these and throw some limits on there, asking you a limit as x goes to positive infinity or negative infinity, just to see if you remember how to go through some of those things. Read these graphs and read those limits. They're going to keep on coming up throughout the rest of this course. And then the very last piece is just, can you evaluate a logarithm? And in order to do these, I mean, this is a math teacher saying it, but they're actually quite simple once you know what to look for. And that's why I put 12 of these on here, because you start getting used to the process of what are we really looking at with all of these logarithms. And once you know that question that you're trying to answer, they're not too tough. So for number 35, in fact 35 through 38 are all very much related to each other. We have a log of 10. Now you need to be able to do this without a calculator. So to find the log of 10, the first thing you need to recognize is that this is a base of 10. When it's not written, the assumption is that it's a base 10. And suppose that log base 10 of 10 equals some number x, whatever it happens to be. The type of problem we're working with here, these logarithms, are basically saying that 10 raised to the x power is equal to the inside of that logarithm, that 10. For number 36, this is a base 10. We're saying that 10 to what power is equal to 100. For number 37, this is base 10. We're looking at 10 to what power gives us 1,000. So every time we're just wrapping around that equals sign. Number 38, we have a base 10. 10 to what power gives us 10,000? Well, these are all things that you should know pretty easily. 10 to what power gives us 10? That's just an x equals 1. So log of 10 is equal to 1. 10 to the x equals 100. Well, that's the second power. 10 squared is 100, so that logarithm is equal to 2. 37, 10 to what power is 1,000? Well, that's 10 to the third, so that logarithm is equal to 3. And then finally, 38, log of what? 10,000? 10 to the fourth power is 10,000. So if you just recognize that we're trying to figure out that base raised to what power gives us the inside, then all these answers are just some number. So let's apply this to a few other kind of problems. So 39, log base 3 of 9. This log base 3 of 9 is asking us 3 raised to what power is going to give us 9. Hopefully you can notice that that is 2. So log base 3 of 9 is equal to 2. 40, 6 to what power is going to give us 36? Wrapping around that equals sign. Well, of course, this is 6 squared. And so log base 6 of 36 is 2. Notice that the log base 3 of 9 and the log base 6 of 36 both equal 2. They're the same thing, just with a different base. 3 to the x equals 9, 6 to the x equals 36. Both get 2. 41, we get 2 to what power is 32? You might have to count on your fingers for some of these, but you do get 5 for that one. 2 times 2 times 2 times 2 times 2 is 32. 42, 4 to what power gives us 64? That is 4 to the third power. 4 to the third power is 64. 43, log base 14 of 1. Same question, 14 to what power gives us 1? Now don't be thrown off by this one too much. Remember, anything raised to the 0 power gives us 1. Which means the log base 14 of 1 is equal to 0. So anytime we take the log of 1, no matter what the base is, that's going to equal 0. For 44, log base 11 of 11. 11 to what power gives us 11? We do just get 1 for that. 11 to the first power. 45, natural log of e. Remember, natural log is a base of e. And so if we rewrite this, we get e to what power gives us e. Kind of like the problem right before, this is just an x equals 1. So the natural log of e is always 1. It just cancels out. I think like number 44, log base 11 of 11, you had a similar one like that earlier in the review packet, where you had a log base 4 of 4 on the expanding and condensing stuff. Make sure you can simplify those. Log base 4 of 4 you should be able to do. It's just 1. And then 46, the natural log of e squared. So we get e to what power is e squared? And just by looking at that equation, we should be able to see that we get x equals 2.